So far, we have given the general idea of how deep learning works, how we feed deep learning models to our data. We have said that first we have a training data that we use to fit our model to that training data. And then later we see if that model works correctly with the testing data. But let's focus on this video in this first step, in the training step. How do we feed models to our data? Before we go into these very huge deep learning models, we will do that too. But before we do that, let's focus on the problem of fitting some models to some data, and let's see some slightly simpler examples for that. In order to do that, we are going to use one Jupyter notebook that we have in our course for drone image processing for forest applications. You will have the link to this course in the notes for the video, and notice that if you don't know Python and want to learn, you have lots and lots and lots of units from, let's say, zero Python to the notebooks that we will be using today, and that hopefully we will keep adding some more content. So today we're going to be using this notebook called Fitting Models to Data in PyTorch. PyTorch is one library, one collection of algorithms in Python. Python is a very useful programming language for data science. In order to be able to show how specifically we fit model to our data, we are going to need data. And before we use the fancy images that we will use for the real problems here, we will define a function to generate our data, and we will make some simple data. If you know programming, you see that this is a very simple for loop, and in this case we are taking a list of coefficients of a polynomial and we are creating some data. If I give it two coefficients, so the independent term and the linear term, so something that would be described with this equation, I get a line that I'm computing all the points distributed along a line and showing them here. You might be wondering, hey, those guys don't form a line. No, to make things a little bit more interesting, I have added a noise step here. So they don't exactly form a line, they are a little bit noisily along a line, okay? Using our function a little bit more, and don't worry if you don't follow this precisely, if we give it three coefficients, then we generate something that follows a quadratic distribution, parabola, okay? Again, noisy, and so on and so forth. We can do this with as many coefficients for our polynomial as we want, and in this case we will stop with the last one where we will create a cubic distribution. Okay, computing, picturing all of the data. Now we will try, now that we have some data, we will try and succeed, hopefully, because this has been prepared beforehand. We will use PyTorch to fit a model to this data. First of all, I want to say that this is a much simpler problem than we usually deal with. For example, let's consider just the linear data. You have seen this, you have done this before. This is just linear regression. If we decide that we know that this data has a linear dependence minus the noise, so a good model to fit here is just a line. And you might have seen this in high school or university, how to fit a line to a noisy distribution of points that follow more or less a linear tendency. So those explaining one of the variables in function of the other when the two have a linear dependence. That's called usually linear regression, and that's what we will be doing here. But probably you have seen an iterative process to compute the two parameters that define a line, and here we will implement very simply that model, that linear model, using PyTorch. Okay. Here we need some math. Before, let me say that we will define a model that will be just a model of a line. So we'll get some parameters, and those will be multiplied. The first one will be multiplied times x, and the second one will be added. So we will define a model, in our case, to fit to our linear data that will be linear. So it will just represent the equation of a line. Okay, like when we generated the data, we had the equation of one line, and now we will find a parameter, sorry, we will define a model that will hopefully reproduce that same type of model. Okay, now, as I said, we need to get a little bit into the math of the whole thing. I need to feed my model to my data. What will be my model? In this first case, it will be a line. And what does fitting the model to the data mean? Well, I want my model, the model that I defined, to be as close to the data as possible. In my model, I will predict a value for y, for every possible x, and I want that predicted value for y to be as close as possible as the real value for y in my data. Okay, and what does as close as possible mean? Well, I can define in many ways how close my predicted data is to my real data, but one very commonly used way is to define the sum of the squared errors, or MSE, mean square error. Okay, for now the sum, the mean squared error. So I will try to set different lines on my linear data. For every value of x that I enter to my model, I will get a value of I, and I will subtract my prediction from the real value, square the whole thing, and then I will do it for all my data points, and then just take the mean. And that will be the error of my line, and I will see if I'm very close to the real data in terms of this MSE metric or not. And that's what I want to make as small as possible. So fitting my model means making some predictions, putting the line at some point, using it to make predictions on my data, and computing the MSE value and making it as small as possible. Okay, great. Now I know in general what I am doing, but I want to implement this. I want to be able to define an algorithm and implement it in the computer and tell the computer what it has to do. And to do this, I will need to compute the minimum of this function. This function that tells me how far I am, how far my model is from my data, is called the loss function. And we will note it with an L. Okay? So in general, I will have my data, y, and the data that my model predicts, model of ax. Okay? And what I will want to make minimal is the loss in I. The loss in my predictions, the difference from my predictions to my data. I want to make that minimal. Whenever I want to make something minimal to find the extreme values in a function, I use derivatives. You probably remember that from high school too. I want to find the maximum values or the minimum values in a function. I need to compute its derivative and find the zeros in the derivative. So here it's the same. Only when I say derivative, I am talking about a function with just one variable. And for example, here I have two. Okay, sorry, not here. My model, here I have two. I have A and B. Okay. So, whenever I want to compute the minimum value of a function that has more than one variable, I have to compute its derivative, but I don't call them derivatives because the function has more than one variable. I can derive it in regards to its different variables. So I need to compute a vector with the derivative of the function regarding each of its variables, and that vector is called the gradient. Okay, so to sum up, I want to make the loss function the difference between my model and my data as small as possible. And to do that, I need to compute its gradient. Okay, so we have lots of delta here, and I'm sure some of you are getting headaches, but that just means that to compute the minimum of my loss function, to find a place where my loss function is as small as possible, where my data is as close as possible to my model, I need to derive it. And I have said before that my deep learning network is going to be something complex, full of different pieces of different parts. I can read this as function composition. It will have different functions, and the output of one function will be the input of the next, or the output of several functions can be the input of another one. So when I do the gradient, I have to use the chain rule. And here we have a slightly more complex expression that just is meant to say that in order to compute the gradient of my loss function, I need to compute the gradient of my loss function, but also the gradient in the model. And the gradient in the model will be made up of lots and lots of small pieces of all the gradients, all the derivatives of all the small parts of the model, all the functions that make up the model. Okay? I wouldn't say this is conceptually super difficult. It's just using derivatives. Fundamentally is what you did in high school class in optimization in math, when you found the zeros of derivatives. Implementing this can be very convoluted, and especially if the networks are big, these derivatives can be very, very, very complex to compute. It can be take a long time. Lucky for us, we don't have to. Computing this very annoying long chains of derivative is what PyTorch does. PyTorch main module is called AutoGrad, so auto gradient, and it computes automatically the derivatives of deep learning models or any other models. Okay, so I want to fit my model to my data. I will need to compute the gradients of the loss function. Let's go do it. First, let me just use some code to see some code and some plotting functions that I have defined. See, initially, when I have just defined my model and have given some random values to the line coefficients A and B, what do I get? I get some fit, for example, this one. This is my data, this is the initial position of the model. So we could say that the line doesn't explain the linear data very well. It doesn't follow it. Okay, so this is not a good fit for our data. Good thing that we haven't even started fitting. So let's define a function to fit to our model. Okay. First of all, we will need the model that we want to fit and the data, which will be represented by these x true and y true variables. The model will have some parameters. In the case of the linear model, it will have 2. If the model was more complex, it would have more. In the case of deep learning networks, this is millions of parameters. Today, in this moment, we are working with just 2. I'm going to do an iterative process. If you remember linear regression, you probably remember that you had to do things over and over again until you reach some criterion. So I'm going to do the same. And I'm going to need a function, which I'm going to call the loss function, to tell me how far or how close I am to my model. My data is to my model. And I'm going to use the MSE function that we defined before. Okay. Slowly defining this fit function a little bit more, I said I would have an iterative process. So that's the first thing that we do. And in Python, we do iterative process using for loops. If you don't know what I'm talking about, don't worry too much about it, but do go and study some Python, because that's going to help you a lot. If you know Python, this is a very simple type of loop. What do I have to do to fit my model? I always follow 3 steps. First, at the current position of my model, I make some predictions. Then I see whether or not I'm close or far to the model. I compute the loss function. Sorry, my model is close or far to the data, so I compute the loss function. And in a third step, I will compute the next set of parameters. I will change my parameters, the parameters of my model, so they fit better my data using the loss function that I have just computed. So in order to make predictions, I just apply my model to the current data and parameters. Then I compute the loss between the predicted data and the true data. And then just down here, I'm going to use the gradients that I have computed for my parameters. Parameters are part of the model. When I said before that I was going to do complex chain rule derivative, that is where I'm doing them. I'm first telling PyTorch, hey PyTorch, helpfully compute the derivative, and the derivative is called backward, of my whole loss function. And when PyTorch does that, very helpfully also at the same time computes the derivative of all the small parts that make up the model that then is used with the loss function. So when I do loss backward, I'm computing the derivative, the gradient of the loss function, but also of the whole model and every small part of the model. And here I'm using the gradients that I have computed to update the parameters. And another variable used in the loop called learning rate that I can set different steps and so on and so forth. Okay, so I have an iterative process. First I make predictions, then I compute the loss, and then I use the gradients. I compute the derivative of everything, and I use those to decide a new set of parameters. Okay, that's the way it works. And I'm going to just use this function to fit the model. Sorry, name fit is not defined. That's the beauty of code. Sometimes you get errors, but if you study enough, you can fix them pretty fast. Okay, so in this moment, I already did linear regression, and this is the result that I got. Okay, I got a very nice line that fits my linear data very, very well. Okay, I will show you some technical things here. I'm at each point I'm storing the value of the loss function, and I can show them here. And you can see that the loss function goes getting smaller and smaller and smaller. Okay, because every time I started with my line here, I end up with my line here, and we will see the process in a second. But thanks to this fitting process, I was able to get my model very, very close to the data. One technical thing that's important here is that because this learning rate is smaller than 1, and I'm making my loss smaller and smaller and smaller, the steps, the changes in my parameters become smaller as the process goes on and on. Okay, so let's see that in a small video. Here you have some code that you can use to generate this animation, but I did that before and I just uploaded it to a YouTube video, and you can see the different positions of the line, and you can see that at first the line moves very, very fast, and it goes getting closer and closer to the data, and as time goes the movements become smaller and smaller and smaller because the change depends on the loss function, and the loss function keeps getting smaller. So steps at the start of my iteration are very big, and then they become smaller and smaller and smaller. And this thing is still moving. Okay, I'm going to try to move it along a little bit, and probably you see that I have fit it a little bit better. You can see this on your own. Let me jump just to the end. Okay, and here I have again a very, very good fit for my data. Notice that this fit is not exactly the same that we have above, because every time we run the code we get slightly different data. Okay. But here we have the code to do linear regression in PyTorch. Basically, we have defined a very simple model that only had 2 parameters, the linear model. Let me see where I have the linear model. Here, okay? We have also defined a loss function that tells us how far the data is from our model. And then we have taken some time to define a function to fit the model to our data. This is an iterative process, make prediction, calculate the loss, and use that loss to update the parameters. This is how deep learning works. And we will see in a future video how to fit a deep learning model to solve the problem of telling whether one image belongs to one among 6 possible bush types. Very difficult image recognition problem, and we will use this same structure. And the code will just be a little bit more complicated, but not that much, and it will have these 3 exactly identical steps. With a more complicated model to solve that problem, we will not be able to just set a line. Okay, so sorry, the model will not be as simple. It will be a much more complex model, one of those models with millions of parameters, but the idea, what we will be doing, will be exactly the same.